All right. So let's go ahead and look up our practice exam. Let's see. Oh, study guide. I had it over here. So let's go ahead and I think we were looking at the Harvard final exam. And I'm gonna have to get rid of. I'll have to replace these in like next semester because some of these I just want to straight up steal. So this was the insert. Right. So we went over. Did we go over this one? The Huffman tree question from them? No. We went over this one. I remember going over this one a couple times. Yeah. So we didn't go over the Huffman tree. So I think this is a good place to pick up. Okay. So a Huffman tree is constructed from a text document that contains 5 characters. I suppose it means it contains 5 different types of characters as opposed to only 5 characters. So the character E appears the most frequently, and the character I has the next highest frequency. Which of the following could be a Huffman tree for this document? 1, 2, or 3, right? So, and then it's got 1 only, 2 only, either 2 or 3, or none of these. So let's look at these. Could 1 be a Huffman tree, with E being the most frequent character and I being the second most frequent character? No. Why is this not an appropriate Huffman tree?
Yeah. There's no way to access the letters below it because E and I are both a single bit.
Right. E and I are both a single bit, and not only that, like this, but that's the reason why. And the reason why is because I and T are internal nodes, and for it to be a Huffman tree, as you can see in 2 and 3, you have to be external nodes. You have to, all the letters have to be on leaves, right? All the symbols have to be on leaves. So let's look at number 2. Could that possibly be the Huffman tree? E is E has to be the most frequent character, meaning the least number of bits, and then I has to be the next most frequent character. So does 2 work? Possibly. Yeah, it works because E is the most frequent character and I has the same number of bits. So it could work. So it could be a tree. This works with the I being the second most number of bits, as well as like the least number of bits, right? Most number of characters. Also, this would also work for if I had the same number as the rest of them, or if I had the least number, right? It also works if I is the second most, right? We just don't know what the counts of TOS and S are, but this would work. What about number 3? E the most frequent character and I the most frequent character. So this doesn't work because E and I, they take 3 bits, and that means that they'd be the least frequent characters. So that doesn't work for these. So only 2 would work for these. And this one's even iffy on itself, but honestly, this is our best answer because it's potential that basically that this one, right, you could have like 5 million E's and like 8 I's and then 1 of each of these characters. Yes?
And since E is the most frequent character, it's always going to be on the left because the top is the sum of all of them. And then
yep. Well, it wouldn't necessarily always be on the left. It's possible that basically that if the sum, if this was bigger than the number of times E's appeared, so if E appeared 10 times and the sum of them appeared 8 times, then this could be on the right and E would be on the left because it would go. So it's possible so it's really just it's possible that it can end up that way.
Okay. But it would be on either side of the group.
Right. I mean, and if, for example, though, it's also possible that, let me go and just clarify this because if you're the only one, you're not the only one with this question. Sorry. Documents. Right. If we look at Kaufman slides, right, on chapter 7, right, and we look at the character counts where we did the normalized count of all. Oh, this is hash codes. So if we look at the normalized count of all the English characters, so basically where, we look at all the, sorry, let me just get to that slide. So it did a frequency count of all the characters in the English language and then normalized it. So the least common character appeared only once. So space occurred with 186 and E was 103. And if we look, space and E take 3 bits because they build up, because there's so many characters that they build up into trees that have their own subtrees as opposed to them being on leaves. That make sense? Right, and over here, like the leastmost, they were all one character. They all had one character count. So these two got merged together, then these two got merged together, and then they got merged together into a single tree, right? Where so they each would have had, if this was the only bit of the tree, this would have had, only 2 bits, right? That makes sense. So it doesn't. The most common character just doesn't always have to have 1 bit. In this one, it made, that's why we can ask a question like this: are these possible trees? All right. So let's see. An array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm, constructing the heap, which is a possible ordering for the array? All right. So we've got. Remember, when you do a heap sort, we take the array and we turn it into a what? A max heap. So over here we have a bunch of heaps. So we can rule out D because that's a min heap, right? D is a min heap since since index 0 is the most. It's the it's the least common. Sorry, it's the smallest element in there. So we need so we're looking for something that is so it's looking for a possible ordering of the array. In other words, it's looking for a max heap. And remember, you can construct. It's possible for a max heap to look a bunch of different ways. So we're just looking for one of these that fulfills the max heap property. So 85 is bigger than its children, 78 and 45. 78 is at index 1, so its children are going to be over here. Is bigger than both of those. 45 is not bigger than both of its children, though, right? How do I know what its children's are, right? Its children are at index, what? It's twice my index plus 1 and twice my index plus 2. So I'm on index 2 over here, so I'm looking at index 5 and 6, right? Indices 5 and 6 right over here, right? So this isn't a max heap. I'm bigger than both my children, and my child is bigger than both. And he's bigger than both his children, and he's bigger than both his children. So that's a possible ordering. 85, 78 is bigger than both his children, but 49 is smaller than both his, so that's not going to work. And then over here, I'm bigger than both my children. 51 is bigger than. Oh wait, no, it's not. It's not. 53 is bigger than that, so that's not a good one. So this was the only valid one. All right. So this binary tree was constructed by inserting a sequence of items into an empty tree. Okay, which of the following input sequences does not produce this binary search tree? Okay, so we're adding items into a tree, and we get this. So what doesn't produce this binary search tree? Well, we've got 5 inserted first for all of them, so that seems to go fine. And then 3 or 9 works for all of these. Okay, 4 over here would do 5, 3, not 4, so that's fine. 3 on the second one, and then 7, boom, boom, boom. So let's take a look at these individually. So we've got 5, 3, 4, 9, then 12, that's fine, then 7, that's fine, then 8, 6, and 20. So A works. 5, 3, 9, 7. 6 works next, and then 12. Oh, sorry, 6, 8, 4, 12, 20. That works too. 5, 9, 7, 8, 6, 12, 20, 3, 4. That works too. 5, 9, 7, 8, 6, 12, 20, 3. I already did that one. 5, 9, 7, 3, 8, 12, 6, 4, 20. That works as well. So let's look at E. 5, 9, 3, 6, Oh, there we go. 5, 9, 3, 6. So that one won't work. All right. So answer three of the four questions in the space provided. You are welcome to try all four, but please indicate which three you care about. Which three you want graded. So 7 points for tree. Suppose the keys of the middle row of the standard keyboard, ASDF, GH, JKL, are inserted in succession into an empty binary search tree. Draw the tree after you make all those insertions. Okay? I'm assuming this is a binary. Yeah, I mean, come on. So let's go ahead and see that. So, this is dry. So A. There isn't going to be a question like this on the exam, but A, S, D, F, right? And then G, H, J, K, L, right?
This is a terrible binary tree.
It is. This is why its next question was, suppose you insert them into an initially empty 2-3 tree, which is one of those self-balancing trees, I believe. So then diagram it to show it before and after the splits. This one, on the other hand, the next one is much more promising. Okay, hashing, 15 points total. So you are given a empty hash table of size 7 that uses open addressing. Okay? The following sequence of keys is to be inserted. 15, 17, 8, 23, 3, and 5. Insert those keys using each of the following approaches. If an overflow occurs, in other words, a collision, indicate where that caused an overflow. So let's go ahead and see. So our hashing algorithm, so it's telling us what our hashing function is each of these and how to resolve it. Linear probing. So our hash function is modding by 7, which is the size of the table, right? So no need to mod it again. And then inserting the and then resolve any problems with linear probing. So let's go ahead and just list our indices over here. So we've got 0, 1, 2, 3, 4, 5, 6. Okay. So 15 mod 7 gives us what? I believe 1. Right? 15 mod 7 gives us 1. So we'll put 15 into index 1. Okay, 17 should go into, so 15, 16, 17 would go into here. Okay, 8 mod 7 gives us 1, so we get a collision over here. So we get a collision and we put 8 into here. That's just simply how I'm interpreting how to do that, but I'm noting that we have a collision there. 23, if we do 23, that has a index of, 23 mod 7 is what? 2. So 23 would go into here, right? So then linear probing would look over here, collision, and until we got over here into that spot, right? That's what linear probing does. 3 mod 7 gets us into here, but we get a collision followed by another collision, so we'd have to take this spot, and finally 5, where we'd get a collision and have to put it into here. All right. So our next problem is do the same numbers with the same function, but we're going to resolve our collisions using quadratic probing, right? Which we've mentioned but never really done, right? What does quadratic probing mean? It's not going to be on the exam, but it's worthwhile to know. Yes.
Just a guess, but instead of adding 1 to x, you square x?
Yes. So, well, you instead of adding, close. I mean, I get what you're saying, which is instead of adding 1, instead of looking 1 away, we look, and then 2, and then 3, we're looking at 1 squared, then 2 squared, then 3 squared away for our space, right? And we still have to wrap around. The reason you do this is because it produces less clumpy hash tables. The downside is that you end up with more with having to do more calculations potentially, because you aren't going to necessarily find a space as quickly if the hash table is really full, and the calculation is a bit more expensive because you're doing a couple multiplication additional multiplication operation there. So all right, so to do this we have the same ones. So 15 mod 7, that brings us into 1 again. 17 mod 7 brings us to index 3. 8 mod 7 goes here, right? And then we're going to look at 1 squared away. So that brings us over to here. Then, let's see, 23 mod 7 gives us index 2, which would go over here. Right, so 23, you would look 1 away, okay, and then we'd look 4 away. So 1, 2, 3, 4. So 23 now goes over here into index 6, right? So I'm just going to put x23 over there just to indicate there was a collision with 23. 3 mod 7 brings me to here, right? So I look 1 squared away, and I'll go over here. And then 5 mod 7 brings me to index 5. So I can put that. I had 1 more collision over there, and that was with 8. So we had only 3 collisions that time because we were able to get 5 into a spot much easier. There's also something with double hashing, which we didn't go over, which basically, if you have a collision, use the second hash function instead. Let's go, but that's not going to be exam, so let's go over this graph algorithm that will be on the exam. And I just didn't want to hit these problems on Wednesday because we had just gone over them. So I wanted to give them time to settle so that we could go over them again, right? Repeated it, you want to be able to do this a couple more times. So here's a graph. Perform a depth first traversal of the graph shown above, starting with vertex C. Select the smallest edge first to break your when appropriate. In the space below, list the vertices in the order in which they are visited. In other words, the order in which we put them onto our stack, not the order in which we pop them off our stack. Okay? In other words, the order in which you go down them. So, right, it's saying, and the way they are able to do this and give you only one answer, because instead of randomly selecting an edge, we're just going to select the smallest edge as the one to travel along first. Make sense? Okay. So I'll put this up here so that you guys have a reference for it, and then I'll capture it. So we've got, so we need our scene and our stack, and we want our output is that the order in which we're visiting them. But the stack's also going to be equivalent to the order that we've seen them, so we don't need to really keep track of them. So we're going to start off with C and put that into our stack, and then we have 3 edges that we can connect to. So we have 5, 22, and 30 are the weights. So we're going to choose the smallest weight, and we're going to go to B. So we've seen B. So now we're at B. Okay. Then B has 4 edges. We've seen C already, so we're not going to consider this edge again. So we've got 18, 20, and 13. 13 is the smallest, which goes to A. So we'll go there. A has 2 edges. We've seen 1 already, so we're going to go to 10. So we're going to go across the 10 edge to D. Okay, and we're at a dead end now because we've seen those 2 guys, right? So what we do is we pop off the stack and look at the top of it to know where we are. We're at A. We can't go anywhere new from A, so we pop off the stack and go back to B. We've seen A and C, right? But we haven't gone to F or E yet, so we'll select to go to F next because that has the smallest weight. So that goes onto our stack. And going to F, does what? We're at a dead end now, right? Because we've seen C, so we pop off F. We check the top of our stack to know where we are. We're at B. So is there anywhere new we can go from B? Yes, there is, to E. So if we put that onto the left of the stack. Now, technically, because we visited all the nodes now, we're done. But the algorithm doesn't necessarily know that. It just says we're at a dead end at E, so we pop. We're at a dead end with B, so we pop. And we're at a dead end with C, so we pop. And now, since the stack is empty, we know we're done. Right? So that's their answer. So now, same thing, but with a breadth first search. Okay? Smallest edge when appropriate. So breadth first. And remember, difference between depth first and breadth first is that rather than using a stack, we're going to use a queue. And again, so what we do with breadth first search is that we start out with C, we put that into our queue, we dequeue to get where we're at. So we have two edges, and we're going to just visit them in the order which is the shortest. So we're going to visit B first, and then we're going to visit F first. F next. Okay? So now we visit B. Is there anywhere near new we can go from B? Well, we could go to F, but we've already seen it. And then we've got A and E. So A and E are the next thing. So we put A down, and then E down. Now we're at F. Is there anywhere new we can travel from F? And the reason I'm not doing the scene queue and a visited output is because they're going to be the same order, right? In reality, of course, because scene will be a set, and you can't control the order of stuff in a set, you'll want an output that's a list, right? So we're at F. There was nothing new to visit at F. So now we need to go and see A. Is there anything new from A? Yes, there's D. Okay, let me put that onto the queue. Is there anywhere new we can travel from E? No. Is there anything new where we can travel from D? No. So we're done here. So the order is C, B, F, A, E, D. Right? And that makes sense. We start at C, then we saw C's up. Oh, I forgot about this edge. I forgot that I didn't see this edge initially. Right? Definitely why you want to check for your answers. So now let's redo this without the mistake, right? Does everybody see that I missed that edge? That C was connected to 3 nodes or not 2, right? So let's redo this. Sometimes it happens. C. So we're starting at C. Okay. So now we have 3 neighbors, and we want to visit them in the order B, E, and F. Okay, now we're at B. Is there anywhere new I can visit from B? No, there's not. Except for A.
Wait, from B?
From B.
And D?
And D.
Also,
Yep, D and B. So B can visit 13 and D at 17. Okay? And then essentially we'll pop off B and there's nobody new to add. Then E, there's nobody to add. F, there's nobody to add. A, there's nobody to add. And D, there's nobody to add. So visit B, E, F, and then the nodes you can get to from D, which are A and D. Next. And of course, the next problem is Dijkstra's to find the shortest path from D to E. List in the order in which they become known all vertices to which the shortest path is determined, and the length of the shortest path for each of those vertices. All right, so Dijkstra's algorithms, and we're trying to go figure out from D to E. That's no problem. That just means we're starting from D, and then we're going to figure everything else out. Okay? I mean, technically, at this point, though, we can stop once we know the shortest point is E. Okay? So so D is our starting node, so we're going to keep track of A, B, C. We don't need to do D because we know it. Okay, so those are our nodes. We need to keep track of the distances to them and the predecessors to them. And then it also wanted us to list the order in which we know them, which we figured out the shortest distance to, which isn't too hard. Basically, it's the order in which we basically go through them. So in this question, we're starting with D. So the first thing we do is figure out which nodes we have a distance to. D has a distance to A and B. So I'll put 10 over here and 17 over here. Okay, and then infinity for all the other ones. Their predecessors are all D at the moment. And okay, so which one of these is the smallest? Well, A is, so that's the first thing we're gonna start the algorithm from. So we're starting at A. Does A have any new information for us? A to B. The edge A to B is new. So does 10 plus 13, is that less than what we know how to get to B for? Nope. Okay, so now we're gonna move on to B. Okay, so B has 3 edges that we can use: B to C, B to F, and B to E. So B to C is 5 plus 17 less than infinity. Yes, it is. 5 plus 17 is 22. So we'll get there through B. So B to F is 5 plus 18, which is 23. Is that smaller? Sorry, no, that's 17 plus 18. My bad. 17 plus 18 is 17 plus 18, which is 35. Is that smaller than infinity? Yes, it is. 5, B, and then, sorry, that's F I'm looking at. D to F, that's 35. E, so now 17 plus 20, that's 27. Which is certainly less than infinity. Okay, so now we select the next smallest node, which is C. Okay, so we're at C. So does C to F add anything useful? 22 plus 22. That's 44. That's not smaller than 35, which is what we had there. Sorry, E. It's hard reading it like this. Okay, so C to E, 22 plus 22, that's not going to add anything over to here. And then 30 to get to F from C, that, we're at C, so 22 plus 30, that's going to be 52, which is not less than this, so we don't add any from our information over here. Then we get to E, which was our stopping point, right? And so the shortest distance to E is 27, right? Okay, and then they go over Prim's algorithm and the minimum spanning tree algorithm, which we didn't go over, which is not really that hard. But they're worth, since we have enough time, it's worth mentioning what they are. So one of the other graph algorithms is constructing what's called a minimum spanning tree. Okay. And the idea is essentially you want to create a subset of the edges on the graph so that you only get one edge between any vertice. Okay, so that's what a spanning tree is. It's a subset of edges where there's only one edge between each vertice, and we get all the vertices connected. The cost to create the spanning tree is the sum of the weights of the edges, and the minimum spanning tree is the cheapest one. Now this might seem like a really hard problem to do, but actually it's like one of the easier problems because it's very similar to the Dijkstra, but it's Prim's algorithm discovered by R.C. Prim, and it's pretty easy. What you do is that essentially you have your set of nodes, right? You start out with your starting node, okay? And then what you do is that you look at the cheapest node to connect to your node. Cheapest node from the nodes that are not connected to your connected node, right? So in other words, look at this algorithm. This is the original algorithm, and we're building the spanning tree for it. So we select the cheapest edge, which is 0 to 2, to connect. Okay, and then we continue by just connecting the. So now we need to connect one of these guys to this set, and we do that by choosing the cheapest edge that will connect us. So we've got a cost of 5 here that we could choose, a cost of 5 here we could choose, cost of 5, cost of 5, cost of 6, cost of 4. Oh, 4 looks like the cheapest, so we're going to choose that and connect it. So now, and we just repeat. So we've got 0, 2, and 5 as our edges. So which is the cheapest edge we can select to connect something to us? Well, 2 is the cheapest at this point to connect something new. So we select that one and move that to our set. Now we need to connect either 1 or 4 to our set. So that's the cheapest way. So is this the cheapest way, or this, or this? Well, 5 is the cheapest from 1 to 2. So we select that one. And then we need to connect 4. And we can connect it using the edge using 3, 6, or 5. So we connect it using the edge that has a cost of 3. That's Prim's algorithm. It seems fairly straightforward, right? You just simply select. This is what we call a now the only reason I bring this up is this is an example of what we call a greedy algorithm. Greedy algorithms work pretty well a lot of the time. They work very well in a lot of problems. And what makes it a greedy algorithm is that's an algorithm, and you've got costs. And at each step of and rather than thinking too hard about any future steps, it just looks at what's the cheapest short-term cost right now. Right? It ignores the long-term cost of anything, and it just says, what is the cheapest move I can do right now, right? So in other words, what is the cheapest way I can add a node to the connected set right now? And it just does that over and over again. And it turns out that's actually the most efficient way to do that in that set. Now, for a lot of other algorithms, that's not going to be the most efficient way to do it. But in a lot of algorithms, if it's not the most efficient, then it's at least an efficient way to do it, right? So in other words, doing the thing that minimizes your cost the most right now actually works out pretty well. That's the only reason I want to bring it up, because if you're in IS&T, you might not learn about that. So, all right, let's see. Now complete all the following problems with these. So suppose you have you have a node that looks like this. Now, right, so you have a key and a data, right? So everybody does their binary trees differently. Like we did ours with generics. They didn't use generics at all, so they have to do this whole int key object data, right? So they have to do like key value pairs stored in theirs. In the exam, because I can't assume the classes use generics, I say like they have an info member, which is typically like an int, right? So, but if you use .data or .info or whatever or .item, I'm gonna know what it means for your node. It's fine. And I'll probably rephrase once I send out the exam. I do have the option of like rephrasing the questions so that they're more appropriate to our class, which is what I'll do. But anyway. This is a binary tree. It's got your standard node. So let's see. The following Java method uses recursion to search for a key in a binary search tree whose root node is referenced by the parameter root. So we're looking for a tree through this. In this tree for this key. If it finds the key, it returns the reference to the data. If it doesn't find it, it returns null. So here's the algorithm to search for an object, right? If your root's null, return null. If the key is equal to if the root has the key, we return the data. Otherwise, if it's less than the key, we go to the left. Otherwise, it's right. In the space below, rewrite search so that it uses iteration instead of recursion, right? Which I mentioned was harder to do. So let's try that. Fortunately, I don't need to backtrack at all, really, at this at all. So basically, I can, so I've given this some thought, and let's go ahead and see how we do this. So what I'm going to do is I'll use the root thing, and I'll just simply say while root is not equal to null. That seems like a good point at which to stop, right, my algorithm. Once root is equal to null, I probably want to stop my algorithm. So, and if I get out of this loop at any point, without giving me an answer back, I'll return null, right? That means, right? I'll break out this loop once root is null, right? And then I'll return null. Okay. So now what do I have to do? Well, what I have to do is essentially do this using iteration instead. So, so this already checked if the root is null. So if root dot key is equal to key, they want me to return the data, return root dot data, because that's the way this is the way their algorithms work, right? This is the way their nodes work. Root dot data. Okay. Else, I mean, this one isn't actually hard at all to convert. So else root dot key, sorry, else if root dot key is less than the passing key, actually other way around, if key is less than what we're looking at currently in the root, then in that case I'm going to say root is equal to root dot left, and then else, if it's not the left side, it's got to be the right side. Root is equal to root dot right. So this didn't really feel so this isn't too different than the recursive algorithm, right? I'm just simply iterating through and going down, and I don't have to really keep track of anything in the stack, even though it's a recursive method that I just converted from, because I don't have to backtrack at any point, right? I don't have to backtrack at any point. Okay. Let's see. Let's see. I want to skip that one. 5. Because I want to get into other problems. Suppose you need to maintain a collection of data whose contents are fixed. You need to search for and retrieve existing items, but you never need to add or delete items. So you have a collection of data that we're just looking for, and we don't want to ever modify it. Although the data collection might be quite large, you can assume that it fits in a computer memory. Which of the following data structure is the most efficient for this task? A sorted array, a linked list, a binary search tree, a queue, all above form the same in this case. Well, E and D are, the D automatically makes E wrong, right? Because, well, because we're going to, we never need to add and delete items, but we always need to search for and retrieve items. Queues, you can only look at the very front item, so that's kind of, you know, so a queue's not going to work, so saying all of them is not going to work. So we're left with a sorted array, a linked list, and a binary search tree. So to search for an item in a linked list, that's going to take and time. The linked lists are great if you want to add stuff to the front and ends of it, but if you want to search through it, not so much. So B is wrong. So we're left with A and C. So either a sorted array or a binary search tree. Right, now a sorted array, right, we can do a binary search to go through that, okay? And then a binary search tree, that essentially sorts it already so that it's already in a sorted order that you can do a binary search. But a sorted array would use up less memory. So I would go with the sorted array over a binary search tree. Because the thing about a sorted array is that it's a pain in the butt to insert anything into a sorted array, right? Because it's essentially an array list that just happens to be sorted. So you'd have to transfer everything over. But if you remove the whole constraint of having to add stuff and shift stuff over, then you want to use the sorted array. All right. Given the array of integers shown below, 5, 19, 6, 12, 48, 6, so a bunch of numbers, right? Okay. What is the output of the following statement? So array 2 is equal to array 2 is 3, 2, 2, 3, A2, 2, 3. Okay, So first off, this whole introduction of A2 equals array, that's just setting up an alias, right? These both have the same, are now basically array2 and A2 are now referencing the same array. So any operation where you see array A2, you could automatically just put R there instead. And it's the same, and it's going to mean the same thing. Okay, so, and these all go over index 2 and 3, which are 6 and 12. Right? So that's the only items I really need to keep track of, right? The only things that are happening are happening at 6 and 12. Right? Which I think is the point here, is just trying to make sure you understand that basically that you've got this array here, right? And you've got essentially a reference to it from R. Then you say array A2 is equal to R. Well, A2 is not a new array. It's an array that basically has the same memory location, so it's referenced to the same array that way. And so then we have 5, 19, then we have 6, and then we have 12, and honestly, I don't care anymore after that because there's nothing after that we care about. So take from int 2, so take from 2, store it into 3. Take 6, overwrite 12 over here, and then take this and overwrite it over here, take this and overwrite it over here, so we're done. So 6 and 6. Right? The reason for this is to make sure that this is an easy question, but only if you understand the song and dance that these two things reference the same array, that this is not creating a copy, right? If a binary search tree is not allowed to have duplicates, there's more than one way to delete a node when then we have 2 children. One way involves choosing a replacement from the left subtree. If this is done, which node are we looking for? So when we're deleting a node from the left subtree, so there's more way than one way. So we can get the largest node in the subtree. Yes, definitely the largest node in the subtree. The smallest node in the left subtree, that won't work, right? If we replace the root with you replace a node with the smallest node in the subtree, then it's not going to work out. The root of the left subtree, nope. The next to the smallest node in the subtree, also no. You always want the largest node in your subtree. All right. Which of the following data structures is most appropriate in which you need to efficiently manage key value pairs that are stored on a disk? If you need to store key value pairs in an efficient manner on a disk, I believe that would be a B tree, because that's kind of what they're made for when it involves disks, but we didn't go over B trees. So, which of the state space? Nope, didn't go over that. Which of the that's a fun one. Considering the following recursive method, what is returned by the call recurse7 2? That seems like a good problem, but it's not going to be on the exam. But go ahead. Which of the following sorting algorithms does not require O of n squared steps in the worst case? So which of these is not O of n squared in the worst case scenario? So insertion squared sort is O of n squared in the worst case. Selection sort is O of n squared at the worst case. Heap sort is what? Worst case scenario. Not O of n. No sorting algorithms O of n in the worst case. It's n log n. N log n worst case scenario. Bubble sort is O of n squared. And quick sort is n log n. So heap sort, right, it's n log n because what you're doing is that you take either O of n steps or n log n steps to turn your heap into to turn your array into a heap or your list into a heap, and then you take n log n steps to essentially remove every item from the heap and create your array and your sorted array in reverse order. Okay, so let's go over another one. Let's see this one. Let's see. Oh yeah, this one's a nice one. All right. So, number 6. A priority queue is a data structure that supports, we know what a priority queue, right? We can insert something in to the queue and remove the minimum. Other operations are size, which returns the number of entries in the queue, and is empty, which returns true if it's empty and false otherwise. 2 simple implementations of the priority queue is an unsorted list, where new entries are added into the end, and the sorted list, whose entries are sorted by their key values. So in other words, so fill the following table with the running time of the priority queue operations for using the 2 implementations. You can assume the implementation is done reasonably well. For example, not performing expensive computations and storing instance variables. So I'm not sure what they're asking for necessarily here, because my first instinct is when they're saying sorted, they're referring to a heap, but they actually might mean like things are literally kept in sorted order in a priority queue versus things are kept in an unsorted order, which is a heap, right? Heaps aren't exactly sorted. So if you're trying to figure out the size or if something is empty, in either case, it's for a priority queue, it's going to be constant time, right? You just check, is it empty and how many things are in it. If we're inserting something into a sorted list, right, that's going to take O of n time, right, because we have to find the appropriate place in the list in which to insert it and then shift everything over. For a heap implementation, that's going to take log n time because we're essentially bubbling stuff up, right? We're checking the parent. And then to remove a minimum item in a sorted list, that's going to take constant time over here to remove an item from a sorted list. If we implement it like it's a so it depends on how it can either be constant time or it could be O of n. O of n if you have to shift everything, or constant time if you allow it to do the whole circular queue kind of deal that we learned about in chapter 4. Again, this is one of those things where you have to know what the instructor had taught, and if you didn't, you have to make an argument as to why. But see how I'm arguing each of those points. Whereas if you're using a heap, right, it's going to take log n time to remove something. Let's see. In this course, we studied many different data structures. Here's a list of them. For each of the following applications, indicate which of those data structures would be most suitable and give a brief justification for your choice. So for trees and graphs, describe what information is stored in the vertices and edges. And if the edges are weighted, describe what information is stored in the weights. Okay. So question 2. So we want a data structure that is a map of the Puget Sound Highway system used to display traffic travel times on a web page. The map displays the principal cities, the intersections, the major landmarks, the roads that connect them, and the travel time between those roads. Travel times along the same road may be different in different directions. So what data structure is that? A graph. What are the nodes?
Intersections.
Nodes are intersections or your location. I would say they're your locations, right, that you want to get to. Intersections are kind of those locations. So principal cities, intersections, the major land, basically all the stuff you want to drive to. Nodes are the stuff you want to drive to. And edges are roads. And what are the weights? Travel time. All right. Chessboard. 8x8 board used for a game of chess. Each square is either empty or contains a chess piece. We did this one. What's the best data structure? Which is the best of these to use? A 2D array. All right. A computer model showing the dependencies between the steps needed to assemble a B-787 at Boeing's Everett plant. Dependencies. In other words, what steps need to be done before you can do other steps? Not necessarily, not a tree.
Priority queue.
Not priority queue. Although priority queue isn't a bad guess. They're, in other words, dependencies. They're prerequisites before you can take the next step.
Graph again?
Yeah, it would be a graph again. It's a graph again, specifically. What type of graph? Undirected, directed, or directed acyclic graph? Directed acyclic graph. Because right? You've got dependencies from one graph to another, right, from one step to another. A list of legal words in a Scrabble game. We want to quickly be able to check whether the words used by the player, in fact, do exist. So we could implement that as a list, but it would take a while, a sorted list, but that would take a while. What would you use if you wanted to very quickly check? You could use a binary search tree. That's one way. That will get you down to login time. That's a valid response. And that'll be more efficient in terms of memory than our other option. A hash table. All right, they refer to it as a hash table rather than a map. Constant time. So constant time or login time, both of those are sufficiently fast. Description of the inheritance relationships between classes and interfaces in a Java program. That would be a tree. Yeah, that would be a tree in this case. Although in a tree, wait a second, in a tree, you can't have more than one parent. And that would be fine for classes, but if we're throwing interfaces in the mix, you can implement multiple interfaces. So now you get a multiple parents, which makes you a graph. So this is another directed acyclic graph. The history list recording websites viewed by the user of a web browser. As new sites are visited, they are added to the list. A list also supports the operation of going back and going back and then going forward, right? You know how a history works. So what data structure would you want to use for that? You could use a stack, but you're not going to be able to go. But you'd need another one if you want to go back forward, right? So in this case, I would use a linked list, but I'd say 2 stacks or a linked list. All right. So nodes. Okay, so nodes in a binary tree are represented by BT node, which has an item and a left and right. All right. Complete the definition of the of method BFS below to form a breadth-first traversal of a binary tree and print the node data values in the order they are reached during the search. In your solution, you may create and use whatever instances of other standard data structures, lists, queues, stacks, trees, hash tables, graphs, whatever, and their operations if they are useful without having to give details of the implementation. So in other words, we want to do a breadth-first search of a tree, right? Which is, if we remember from our last lecture, that's a level order traversal, right? So for this one, let's see the code for that. It's not too bad. So we want to do a breadth first search, and I'm going to assume I want to visit my left before I visit my right. Okay, so in that case, I'm just going to create a queue. See, queue is equal to new. Technically, you have to make a linked list for a queue if we're doing Java, but you could put queue there because I believe queue is an interface. Whatever. Okay. And then I'm going to throw the root node in that queue. So queue dot, and if you put enqueue here, which is what I prefer to do, into, as opposed to like, I believe the proper term in Java is offer, but if you use the other term, it's fine. Okay, offer this to the queue. While, and I don't need a set here because because the direction, visiting my children is a one-way direction, so I don't have to worry about, going over the same node twice. So while queue dot is empty not. So while the queue is not empty, what am I going to do? I am going to queue dot, let's say node, and do BT node. So BT node current is equal to queue dot poll if current dot left is not null, not equal to null, q dot offer current dot left. I'm going to be lazy over here and say same but right child to be same but right child, right? So if it exists, I'm going to add it, and if my right child exists, I'm also going to add it. And I guess then what am I supposed to do? I guess it says I want to print them out. So s out current the values. Yeah, current dot item is what they have in there. And then I'm done. So that's really all you have to do for that problem. The tree problems are all going to be fairly short. Right? If you understand recursion or just how to traverse them, it's all going to be fairly short. All right. Another graph problem. Here's an adjacency list representation of a directed graph where there's no weights. Okay? So here's an adjacency list. Okay? So we've got A, and then this is a linked. So A's at, this is like the keys, and then we have a linked list representing the values for the adjacency list. So we have A, which has B, C, D, B to A. Right, so this is a directed graph, no edges. Draw a picture of the directed graph. It's not too bad. So we know we have 4 nodes, A, B, C, and D. So we'll go ahead and draw them. A, B, C, and D. Okay, and now let's look at A. A is connected to B, C, and D. Right, A is not connected to B, then C, then D. It's a linked list of all the nodes it's connected to. So A is connected to B, connected to D, or C and D. B is connected to A. C is connected to B. And C is connected to D. And then that's it. Another way to represent a graph is an adjacency matrix. Draw the adjacency matrix for this graph. Okay, so let's translate this into adjacency matrix. Okay, we don't even need the graph to look at. So here we'll use 1s and 0s to represent whether or not an edge exists. So adjacency matrix looks like this: A, B, C, and D. A, B, C, and D. So we've got so nothing has an edge between itself. A has an edge to B, C, and D. B has an edge to A, but nothing else. C has an edge to B and D, but nothing else. And D has edges that go to nothing. So it's not exactly the hardest thing, and taking this into and turning this into a graph is also fairly straightforward, right? A has edges going to B, C, and D. B has an edge to A. C has an edge to B and D. And D doesn't connect to anything. But knowing how to translate how those work is pretty important. Consider the following directed graph. Oh, it's weighted. That means they want us to do Dijkstra's. We want to do Dijkstra's to determine the shortest path from vertex 1 to all the other vertices. Update the entries in the following table to indicate the current shortest known distance. Okay, from the predecessor vertex from 1 to each as the algorithm progresses. So below the table are shown as they added to the cloud of known vertices as the algorithm. So in other words, complete the table for the vertices and list the vertices as they're processed by the algorithm. Okay, so this is just Dijkstra's algorithm again, right? So we're starting from 1 Okay. So we've got nodes. So we care about nodes 2, 3, 4, 5, and 6. So here's our nodes. We want to know the distance to them. We want to know their predecessor. And then it also, this one is one of those other problems where they want to know the order that we visited them in, right? The order in which we figured out the shortest distance to them. So nodes 2, 3, 4, 5, and 6. Our distances, our initial distances are what? We've got 2 and 4 that were connected. So 1 to 2 has a distance of 2. 1 to 4 has a distance of 3. And then these guys have a distance of infinity, infinity, and infinity. And we also have a predecessor. Everybody has 1 as their predecessor. Okay, so which of these is the smallest to get to? 2 is the smallest to get to. So that's the first thing we visit. So from 2, we can get to 5 and 3, which are not already gotten to. So we just simply add the cost of getting to 2 to the cost of getting to 5 or to 3. So 2 plus 3 is 5, so the cost to get to 5 is 5. And the cost to get to, and we got there from 2. And the cost to get to 3 is 2 plus 5, which is 8. 3. This is why I hate it when they use numbers as their vertices, because you're having to juggle distances and the names of the nodes. So which of these is the smallest now? 4 is the smallest. So we'll go and visit 4 next. Okay, from 4, it costs. And it only gives us one new thing. It gives us the edge 4 to 3 with a cost of 1. So it's 3 plus 1 less than the current cost I have to get to 3. 4 is less than the current cost I have to get to 3, so I'll put down 4 as the predecessor and 4 as the distance because that's 3 plus 1. Okay, so now we've got 4, 5, and infinity. So this is the smallest one, so I'm going to process 3 next. So 3 has only one additional edge that's useful, which is 3 to 6. 3 to 6 is 2. The cost to get to 3 is 4, plus 2 to get to 6 is 6 less than infinity. Yes, it is. Put that down as 6. We got there from 3. Okay, now I select this next sheet of this. 5. Is there any new edges from going from 5? 4. So cost to get to 5 is 5. And adding 4 to get to 6 is a total cost of 9. Is 9 less than 6? Nope. So we're done. So that doesn't update. So we're done here. All right. So if V is the number of vertices in the directed graph and E is the number of edges, what is the running time of Dijkstra's algorithm in big O notation? Give a brief justification for your answer. You should briefly describe any assumptions you're making about the implementation that would affect the answer. That second line is the killer point. So Dijkstra's algorithm, as we're doing it right now, is O of V squared, right? And the reason for this is because we're looking through each of these. So basically, we've got V minus 1 vertices that we're trying to figure out the shortest distances to. For each of those, so we do a loop V minus 1 times. And in each of those loops, we have to look through each of the V minus 1 vertices to figure out which one we have the shortest distance to. And then we do a set number of steps that go over each of the edges. That tackles each edge once, by the way. But why aren't I throwing it in? So why isn't V squared plus E? Well, because the maximum number of edges is what? V squared. So that would just simply be V squared plus V squared on the worst case scenario. So I would say it's O of V squared. All right. A topological sort of a direct baselike graph, a graph without cycles, yields vertices. You know, that tells us about the topological sort. In big O notation, what is the running time of a topological sort? Give a brief but precise answer explanation justifying your answer. So that depends on your implementation again. If we're doing breadth first search, right? Breadth first search is O of E time. Basically, depth first search. If we're doing the depth first search version of it, that takes O of E time, basically, because on the slides it says the algorithm is do a depth first search, get the order which stuff is popped off the graph, and then hand that order to me in reverse, and that's the order in which you want to do stuff. So how long does it take to do depth first search in that case? Well, depth first search is you have to check basically every edge exactly once. Right? You check every edge once. So it would be O of E time. Let's see if I'm right. DFS. Discover financial service. I obviously haven't been doing enough, computer science Googling on this laptop that didn't come. So O of E for E plus V with the explicit graphs traverse without repetition. So O of E plus V. In this, okay. So they say O of E because you also have to visit every vertice as well. Let's see what our slide said just in case, because apparently I got that wrong. Let's see. Because you also have to mark all your vertices as unvisited, and then you have to mark them as visit as well. So basically, once we mark every node as visited, that's O of V time, and then E time to visit every edge, to check every edge. So okay, I can see where they get that. So that's one answer. And besides, you'd have to reverse your list anyway, which would take, which takes, if there's O vertices in there, then, so if there's V vertices in there, it would take O of V time to reverse the list. All right, so what about the cons algorithm, the one we used in class? Well, that one's actually pretty slow, because what we have to do is that we have to check each node. We look through all the vertices and find the ones that have no incoming edges, and then we remove one. And then we look through all the vertices and find the ones that has no incoming edges, and then we remove one, and all these edges. So that takes V squared time to do that, to remove all the nodes. And then we have to to search. So that's O of V squared, because each step, what are we doing? We're removing. We're looking for the node that has no incoming edges, and then to remove one, we have to remove the node plus all the edges that are associated with it. So I'd say that's O of V squared plus E, which again, O of V squared in that case for the worst case scenario. So let's see. Let's see here what we want to do. Actually, it's 1:43, so I'm thinking this is a pretty good place to stop and we'll do one more review on Wednesday for this. I'll focus on a lot more coding on Wednesday.